I've updated the slides. This coefficients was wrong, so it's supposed to be e to the power j omega minus 0.5. The slides have been updated, and now we can continue the next page. In this page, we are going to talk about the relationship between DTFT and DTFS. Remember that if the signal is periodic, we can both use DTFT and DTFS. However, when the signal is not periodic, in this case like half to the power of n un, well, we can approximate it to be periodic if we use large enough sample of n, because look at this. Maybe after about 10 samples, it's almost close to 0. So let's examine what is the DTFS of this sequence. I mean, in this example, we repeat the sequence every 32 samples. In this, we repeat it every 16 samples and 8. And you will see that as the number of samples becomes less, then it didn't go to 0 first before it repeats. So it doesn't basically reflect the actual characteristic of the original xn. And when we use 4, it's even worse. I mean, it didn't even go to 0, which is here. But in this example, we see that once we have used n equals to 16, there's very little difference from using n equals to 16 or 32, at least from this decayed part. Alright, we're going to use n equals to 0 to 15 and compute the DTFS, and then let us see what is the value. What is interesting is this. The red line over here is the DTFT of xn, the aperiodic xn. And here, all these blue lines are the CKs for the C0 to C15. If you count the number of lines, it's exactly 16 lines, dividing 0 to 2 pi into 16 different parts. And what we observe is that the blue dots are touching almost exactly the red dot. And what it says is that actually I mean, if you're not very concerned about that very small error, using, in this example, 16 points, the DTFS is enough to approximate the DTFT of the aperiodic sequence. The other way to look at this is that, can you see that this is from 0 to 2 pi, from 0 to 2 pi, and this 0 to 2 pi, as we have said before, can also be thought of as this circle going from 0 to 2 pi. And when we divide it by 16 different parts, is 2 pi divided by 16, or in this example is 2 pi, I guess it is divided by 8. What we are seeing is that we are dividing this circle into 8 points, and these 8 points are sitting on this circle at this particular angle. And this way of thinking about it is that we are performing a sampled version of the unit circle, and if x of omega is from 0 to 2 pi, then CK is the sampled version at this particular angle only. So again, these two views are actually the same. Here we are unwrapping 0 to 2 pi along the horizontal axis. In here we are seeing the 0 to 2 pi as a circle, and the CKs are situated at this particular point. So this is another nice diagram about the relationship. It is from Fessler, and let us now examine what this diagram tells us. If we have a x of n, we can generate its replica, so periodic sequence x of n, by creating more and more examples of it. Once we have done that, we can perform the DTFS, because only DTFS can be applied on periodic sequence. X of n, we can apply in here, x of n, we can apply the DTFT, so we get x of omega. And when we apply on this line for DFT, we are actually pretending it to be the periodic sequence xk. So remember, DFT is operating on xn directly, n sample, but actually it is pretending it to be periodic. So it learns xk and ck's are basically they are almost the same thing, at least for that n sample. Finally, we said that it can be viewed as a sampling. X of omega is along 0 to 2 pi, while x of k and c of k are actually points on this x of omega at exactly this angle 2 pi over n times k. So this is a sampling of the x omega to get you x of k, or similarly c of k. Now finally, x of n can also be z transform. So this is the big arc over here. By z transform, we get x of z. And if x of z, if we want to convert x of z to x of omega, it is only along the unit circle. And if we want to get from x of z to x of k or c of k, we are sampling along that circle. So this diagram is a very nice diagram showing the relationship of DTFT, DFT, DTFS, as well as the Z transform. Thank you.